Okay, I want to thank everyone here for joining us today. We're going to go ahead and get started. My name is Will Velez, and I'll be joined today by Ozren Veskovich and Ashwin Dua to discuss monitoring dynamic instability in rough load zone on hydrogenerators. Okay, a few things to cover right before we get started. Everyone upon entry is muted, so we're going to have a total of about 30 minutes of presentation. Then after that, we'll have some questions and answers. Please feel free to submit questions through the questions box, and you can submit them at any time during the presentation. We are recording the presentation, and the link will be emailed to everyone in attendance to access the recording as well as a copy of all the slides. You should expect those to go out probably about 24 hours after we conclude the webinar. And if for any reason you don't receive the copy, you need additional assistance, anything like that, you can reach us via email at info@qualitrocorp.com. Any questions can be submitted to the questions box, and any issues that you're having with the webinar itself, you can submit that through the chat function as well. Okay, so without any further ado, I'm happy to announce we're going to get started here. And Ozren, if you want to kick it off, maybe say a little bit about yourself, and let's get this going.
Yeah, thank you very much. Good evening, everybody. I'm Ozren from Vesky, and today I'll be talking about monitoring dynamic behavior of hydrogenerator where it's operating in rough load zone, or it's popularly called also partial load. So just one question before we start. Ashwin, do you want to do any intro, or should I just continue myself?
I can do a quick intro.
Okay,
so, guys, most of you know me. My name is Ashwin Dua. I'm the sales engineer for Western Canada and Western US. And we have Ozren Veskovich, who's a rotating machine expert, and you know, he's an expert on machine condition monitoring in the power generation industry. Most of you have met him. You know, we have traveled with him to your offices. So for a decade, he has been working as a field engineer and mostly performing measurements, troubleshooting issues, and providing technical advice on condition monitoring. And in his current role, he has developed the CODIS platform. You know, this is our software platform that we use for vibration air gap analysis, and that's what he's been involved in developing. Written over 15 technical papers, and very happy to announce that in the last 3 Hydrovisions, he got the Best Paper Awards as well. So that's a great job. So with that, Ozren, you can get started.
All right, thank you very much. So just one thing, I did not get the awards. The team that brought the paper did. So anyway, but we did get the awards. That's true. All right, so today we'll be talking about monitoring the hydrogenerators, and especially in the zone when the hydrogenerators operate and have low frequency problems. So the purpose of this webinar, and any webinar actually, is to introduce the approach that we have on monitoring hydro machines, and also that includes monitoring rough load zone operation. This subject is fairly popular, and you can actually find a lot of good papers on the internet. Some are even more scientific. Some are dealing with the design of the turbines. Some are more practical, like what we'll discuss today. And basically, you can find the correlation between machine dynamics during that operating on partial load. So we have 45 minutes, which is not long. So this is the reason that we will just go, you know, briefly through roughly 30 slides and try to touch the core of the problem in a way. So the agenda will be, what is the rough load zone? Just try to define it a little bit, not very detailed, and then how machine behaves when it operates on a low frequency, on a partial load, and there are low frequencies that occur. Then some monitoring techniques, what and how to measure online, and then we'll try to get some real case studies of what happens in rough load zone operation. So this is roughly the agenda. So when we are talking about a rough load zone, sorry, my slides are okay. So when we're talking about rough load zone, first we'll start with the turbine design. There are different types of turbines. That you probably all know that. Some are designed for high head, and some are designed for low head, and even it also depends on the flow. So we'll be talking about Francis turbines, which are basically somewhere in between the like low and a high head. The reason we'll be talking about those turbines is because they have a fixed blade design, and that's why they cannot operate efficiently on all conditions. And because of that, they do tend to have instability when operating on auto design parameters in a way. So this is just these are just two pictures and schematics of a Francis turbine. So basically, we have a shaft, and then we have the spiral casing, and then we have a runner, guide wings, strain wings, guide wings, runner blades, and then water comes down the draft tube. So, and roughly this is what it looks like. This is the Francis turbine. This is the pump storage or pump turbine. It's a little bit different, more disc-like flat, but this is the Francis turbine, right? So because it has fixed blades, fixed thing, you cannot adjust the pitch like you can on the bulbs. They tend to be unstable in certain areas. So if we would look at a hill chart, this is basically, you can find this on the internet. So you would see that it's designed to have maximum efficiency at a certain flow and certain speed, and out of that you have different problems that might occur. So this is where you should be working, and it's also called when you are observing from the perspective of a rough load zone. This is a rope. We'll again discuss what is the Vortex rope, and then this is what we'll be talking about today. This is where you want to operate your machine, and this is what we're talking about today, because there's a zone in which machines should not operate. Not all the turbines have this problem, but most of the Francis turbines do have problem operating in rough load zones. All right. So that partial load, there is some also called deep partial load and high partial load, but we'll be not talking about it today. We'll be talking about the rough load zone, which is the partial load. So this is the zone. If you observe another type of diagram, this is a zone in which is not recommended to operate a machine. But the boundaries, as you will see today, are not always strict. They can be blurry. So how do you define what's the zone and where to operate? This is what we'll be talking about today. Right? Again, that zone also varies, or depends on varies with water levels. So if you take a few days and you take your tail and head water levels, and then that will affect us again your rough load zone. This is rough load zone is not the same. It depends on the head and also on the power. So the power span basically expands with the different water levels, which you can actually map. So this is it. So this is what we've done in the power plant, a few power plants. This is just one example. So basically, if you have your head and your power, the zone, the lower and upper levels, more the upper level actually changes with the net head, right? So and then vibrations or that low frequency dynamics will not be the same on all in the complete, will not be let's say equally bad in the complete span. So it also depends from the unit to unit, but maybe you'll get a zone like here in which you should not operate, or maybe get a maximum peak or at a certain power versus a certain head in which basically your machine behaves the worst. And then this is just the edge. And those points are connected with the machine response. Actually, these are the points where machine had the response to like where the low frequency dynamics or vibration started and then ended. All right, so that zone is also flexible in a way. It's not fixed. All right, so this is just an intro about the rough flow zone, and you can ask questions later. So how does machine behave when it operates in that power span? So there are two mostly known outcomes of working in a rough flow zone. First one, and everybody knows about it, it's called the vortex rope. It's actually the vortex creates is created under a turbine, which basically rotates, spins on a lower frequency, usually from 0.2 to 0.3 of the nominal frequency. So 20 to 30% of nominal frequency, that's the frequency of that vortex rope wobbling, and that's actually the frequency of the dynamic instability. And then pressure pulsations occur, radial vibrations, shock vibrations, axial vibrations of rotor, drop tube vibrations. You can have power swing. Basically, this is the outcome when you operate in a rough flow zone. Everything becomes unstable on very low frequencies. So that's the effect of rough flow zone. And so we will try to see what's the mechanism behind it. Yeah? So this is all well documented. These are the this is available. You just Google partial load or rough flow zone, you'll get these pictures and basically you'll get a lot of articles about it. So, but what we want to know is how it develops a little bit more. What happens? What precedes to development of rough flow zone, right? And then possible side effects are you can have cracks on the runner blades. You can have cracks in bracket to foundation supports, axial foundation axial brackets. Even the axial truss pad damages. This is what we've seen. So basically, destructive forces appear on low frequencies, and then they're causing fatigue and consequently cracks on machine parts. And low frequency vibrations are, in my opinion, are most destructive because these are very large forces and the machines are very heavy and everything wobbles on low frequency. So it takes a lot of energy to move that machine, right? And that energy comes from somewhere, right? And then I will show this diagram only once. I will not be talking about low frequencies and show you the diagrams that we measure that it occurs on a certain frequency. This is very well documented and mentioned thousands of times when people talk about rough flow zone. So I'm just going to explain this once, and then we'll not be discussing that anymore. So if this is the nominal frequency, let's say this is a spectrum, waterfall spectrum with some power span of the shaft displacements. This is a 1x, so the nominal frequency. This is the 2x, second harmonic, and then this is the frequency, and then we have a shaft displacement. Each of the marks on the y scale should be multiplied by 10. So this is 5, 10, 15, 20, 30, 35 microns. So and in the power span from 10 to, let's say, 18 to 20 megawatts, this machine experienced the low frequency vibrations, and then they're at the peak at some 18, 17, 18 megawatts, 15 to, let's say, 18 megawatts. And this is what actually happens on every machine. So below 1 hertz, usually from 0.2 to 0.3 of nominal frequency, you get this is like 0.3, 0.25, you get the low frequency wobbling, right? And this is what happens. So, and we will not talk about it. I will not show you those pressure pulsations today in this form because everybody knows it happens. So we're going to go a little bit further than that, all right? So we're going to ask the questions. These are the questions that came up to us when we were starting dealing with analyzing those phenomena. Why do vibration occurs on low frequency? What's subharmonics? What causes these vibrations? What is the nature of vibrations? Are they forced? So if they are, what's the force? Or they may be self-excited. So again, what's the cost to self-excite the huge hydrogenerator, right? And which parameters should we monitor to more easily describe what's happening? And maybe try to avoid operating and how to map that rough flow zone. This is what I already explained. What's the polarity edge in which I can operate my machine, or and which is the area which I should really avoid, and how to interpret the data. So these are the key questions that we will try to answer today, right? This is the purpose of this webinar. So what are the monitoring techniques? So when we talk to our customers and we come across various specifications, regardless of the online monitoring or just performing the measurements, this is usually asked. You know, people concentrate on head cover vibrations, which is good. Also draft tube vibrations, turbine bearing vibrations, maybe guide bearing vibrations. Sometimes they add cavitation, because Vortex is also kind of a cavitation phenomena. So this is usually asked, all right? So, but is it really enough? Well, what we think it's not. What we like to do is put some more probes, and which we will discuss during this presentation. We've seen that putting axial displacement on various positions, depending on the machine design, is really the critical part. So obviously you want to monitor your oil film, but you also want to monitor how your rotor completely shifts from concrete foundations, from basically non-axial load part of the construction, and to just see what happens, how the rotor lifts up and down. You also want to see the truss bearing bracket vibrations, and you want to see the axial movement on the turbine cover, and pressure pulsations are also very, very important to this. All right. So, and then this is typically, depending on the machine design, is it umbrella or some other on some other construction, we would like to have also radial vibrations, and basically have we call it holistic approach to monitoring, so we can actually see what's really happening. So because we want to know why it happens. All right. So what types of sensors we use? The proximity probes, just for people that maybe are not really in the measurements. So proximity probes are contactless displacement sensors. You put them on a bracket. Let's say for radial vibrations, you put them on a bearing bracket, and then measures the movement of the shaft to the sensor. Basically, you're monitoring the oil field here. You're just basically moving. One part is moving, the other part is not moving. You're measuring with this sensor how much this part moves to this one. Yeah? And then for accelerometers that we put on the bearings or turbine cover, basically anywhere on the machine, what we really want to have is high sensitivity. So at least 500 millivolts per G, 1,000 millivolts per G is even better. And then it has to go from low frequencies, because remember, the frequencies you're measuring here are 0.5, 0.6, 0.8 hertz. So if your sensor cannot measure on low frequencies and is not sensitive enough to have a noise over signal ratio, then basically you will not be able to process the data properly. So these are for bearing vibrations. This is what we want to have, at least 500 millivolts per G, and then below 0.5, 0.2, 0.1 hertz. You can even find 0.1 hertz accelerometers today. And then you also want to have a flexible and adaptive monitoring platform, which will help you, if necessary, adopt your analysis techniques, because conventional monitoring systems sometimes are not configured properly to catch those low frequency dynamics, which I'll explain later a little bit. Because for low frequencies, you need a longer signal to be able to extract those low frequencies accurately. If your signal is too short, you just don't see the low frequencies below the duration of your signal. So these machines can vibrate on 0.5 hertz, which is very low frequency, and they can spin on, let's say, 3 hertz, which is 6 times more. So if you want to catch, you need to have a longer period of signal. So your monitoring system should be able, but also you want to have fast data processing for normal operations. So you need to have adaptive platform which can do both simultaneously in a way, right? Also, that platform would need to be able to recognize machine operating conditions, and because when you are alarming now, as you will see later, then that alarm has to be properly processed. So if I have a rough load zone and I want to change my alarms, I need to be able to, this device should be able to recognize that operating condition is different and then adapt to that as well, right? So these are basically two things that are very important to when you're processing the data online. So monitoring low frequencies requires longer signal processing, right? So, and then what are the factors that I would use that would really tell me that how severe things are, right? So you can have different types of vibrations measured, but we have been playing with how to really have one number, or so we tested 3 different measurement types and trying to see how they would describe what's really happening and in Ruffle zone, but not outside Ruffle zone. And then we came to this, we call it a factor. The factor is basically the ratio between you take the same signal and you process one signal as you would normally for normal operation of for rotating machines, and you get let's say peak-to-peak number. But then again, you take a longer signal duration and you do the same calculation, and then you divide the 2 numbers. And in the normal operation, so if this is the power, and when you're starting to increase the power, you can see that this factor basically is high, and when it comes to normal operation, full load, it becomes very low. So the idea is that I can trigger the alarm on the factor now, and this will be the really very fast indicator that there is something happening, right? There are other, you can also do the band frequency analysis. That monitoring should be able to do that. So you can just narrow the lower frequency, which is also good. And but for that, you need also longer period of signal. And then there is something we call the rest, which is we extract all the harmonics from the first, second, and third harmonic, which are related to rotating speed, and we just monitor everything else. So that will give us also the higher and lower frequencies. So these are 3 numbers that we usually use to alarm the in Ruffle zone, right? And we extract, basically with that, we extract the influence of the machine rotating frequency, because these are subharmonics that happen here. And then as we decompose the signal properly, we continuously monitor it, and we can trigger the alarm. And basically, you can have a kind of a more secure protection and alarming on your processor than you would have with a conventional monitoring system. So those vectors, we call them vectors because we actually calculate amplitude and phase all the time, and they are continuously evaluated and stored to database, so you can basically easily pick them up from with a historian and just plot it over time. When something happens, when one of those factors trigger the alarming, then we store the raw data. And with that raw data, we have pre-triggering, and then with the raw data, we can do the post-process analysis. We can now go through that event, and we can, as you will see later, change and adapt our analysis fully to get the most out of the signals we recorded. So with those pre-processed signals that I've shown, we want to trigger the relays, the alarms, sorry, and then that alarms will trigger the recording of raw data, and that raw data will be stored with a full maximum sampling frequency, which you will see later how it looks on the graph. So adaptive monitoring, just to show you, if we have a trend, this red represents rotating speed. This is the active power. This is actual displacement. And on the upper diagram, we have a generator guide bearing and turbine guide bearing vibrations. As we are passing through the Ruffle zone, this blue curve here, we have a response to those to the operating Ruffle zone. So we want to adopt our monitoring and say, okay, when in this power span from here to here, I'll have different alarm levels, because this can be 3, 4, 5 times more. This number, the vibration that occur in a Ruffle zone can be 3 to 5 times more than a nominal vibration on nominal power in regular conditions. And so I want to know I don't want to just put the alarm on a very high number, because I want to also protect my machine and monitor it in a normal operating conditions. So I can distinguish between the two, and I can set one alarm for my normal operation, and I can set another alarm for my Ruffle zone. So this is the adaptive monitoring. And this is actually now in the new standards, it's also mentioned that adaptive alarming should be used for this kind of transient conditions. And now we come to this quantification of problems. So actually, what does it mean? So again, we come to these questions. What is really happening? Which parameters should we consider the most, and how to fully understand what's really happening in a rough load zone? So I'll be talking about how you can monitor and what factors to use and what numbers to use and adaptive platform, but what really does happen, because not every machine is the same and it will not always react the same. But we did find a pattern. We recognize the pattern that is really on the we think is it's on the right. We hit the right spot, if you want to say it like that, in what's really happening in rough load zone, right? So and we always have to remember, large low frequency vibrations means that there are large forces involved. So our question is basically what might cause low frequency vibrations. So we believe it's self-exciting, and not just us, but there are also people working on it, and we agree with that theory. And let's just see why we think it's a low frequency. It's basically self-exciting vibrations, right? So we'll be going through different parameters that we think are the key for monitoring that I mentioned in the beginning, and we'll show the graphs and how the machine behaves, right? So first, what came to our attention is that pressure, of course, but also axial position of the machine, axial lift, are correlated. So on the left side, we would have static signal components, which I said are vectors or scalar values. These are computed numbers that I've mentioned before. And this is the raw data, the dynamic signal. So this one has 1 point per second resolution. This one has 1 point per each half millisecond, right? So this is a 2 kilohertz sampling rate, and this is out of this signal we compute those numbers, right? So this is the active power, and this is the pressure. So as the machine passes through a rough load zone, we can see that there's kind of a, this is the power decrease. So the pressure kind of lifts up a little bit. It builds up during the rough load zone. And also what happens in that transient is that the rotor lifts, which I will show you later. So this is the static pressure and a static kind of a static component of an axial lift. Dynamically, as you all know and we mentioned before, on low frequency, it wobbles around that static position, right? So this is the instability. The energy is going up. It's basically causing a pressure pulsations. It's pushing the water up, out and in, out and in. And also axially, the rotor lifts up and down, up and down. So it's basically bouncing off the energy that came from somewhere, right? As statically, it looks like it basically lifts up. And then as it lifts up, it also wobbles on low frequency, right? This is what happens. So pressure correlation between pressure and the axial displacement. This is really important, right? So this is the axial displacement versus the power, X versus Y plot. And the sensor looks in this direction. So that means that when this number decreases, the rotor lifts. Basically, it's pushing up to the sensor. When this number is decreasing, the rotor is moving down. So if we are putting a load, we would expect that the turbine, because of the water pushing it down, would basically move away from the sensor, which the pattern that it should look like this. But what we see that when machine operates in rough load zone, it actually starts to lift. So it lifts, and during the partial load, it's lifted. And then when you get out of the partial load, it again comes to the, basically lowers down, right? So the static axial position, the whole rotor actually lifts when it operates in rough load zone. Even though the power is increasing, it's still to a certain point is lifting, and then it starts to go back. Also in the same period, the pressure pulsation, the static pressure builds up under the turbine, right? And then out of that it goes. So as the water flows through from zero and then to maximum power, the pressure is lowering down, but at a certain area it actually builds up below the turbine and then starts to discharge. So the pressure builds up and the rotor lifts axially during the the rough load zone operation, right? So, and then when you look at the raw data, what actually occurs, these are the shock vibrations on turbine bearing, X and Y. This is the pressure, which we mentioned, raw data. This is the active power, raw data, coming from the current, calculated from currents and voltages. And this is the axial displacement on two positions. This one is the truss bearing axial position, so it measures the lift of the truss bearing to the rotor in the truss bearing, and this one is on a concrete foundations looking at a turbine cover. So what we see during before the machine enters in the low frequency wobbling, the sequence of events is like this. Static pressure builds up during roughly 30 seconds, and the axial position shows that the rotor lifts. So there is correlation between the static pressure under the turbine and the rotor lifting for 50 microns. At that point, first what generates are radial vibrations, not the pressure pulsations, but the radial vibrations. They occur roughly 10 to 15, 20 seconds, sometimes from 5 to 20 seconds, it depends on the machine, before the pressure pulsations under the turbine. So machine starts to basically vibrate radially, and then this phenomenon starts to develop. Then the pressure starts to basically follow that at this point, right? Axial movement, axial vibration starts to occur before, after maybe 10 to 15 seconds after radial vibrations. You can actually see them develop on the low frequency. And then from this point on, everything is simultaneously moving on the low frequency. So this is the phenomenon. So before we got this on the first power plant, we thought that pressure pulsation, and that was a common thought, that pressure pulsations actually develop below the turbine, and then they cause the vibrations. But we actually we have maybe 5 or 6 machines where which we equipped with a configuration I showed you, and then they all show pretty much the same behavior, right? So vibrations start before. So, and the vibrations are counterphased. It depends on the design. Let's say if this is umbrella, we are measuring on a lower guide bearing and a turbine guide bearing, they are counterphased. And then if the truss bearing is below the upper generator bearing or combined, then upper generator bearing vibrations, lower guide generator and turbine guide, they are counterphased. So basically machine tilts around a certain position, all right? Around the center of mass, if you want to call it. So you can see that it's really low frequency. This is one rotation. This green would show you 1 revolution, and this is roughly 6 to 7 revolutions. Low frequency is 6 to 7 revolutions of the machine, so it wobbles around. So when you're observing the shaft displacements, if you're using conventional orbit plots, which are taking a smaller samples period, they basically cannot catch this low frequency phenomenon. You need to have a longer period orbit plot. So when we record the data like this, you can basically choose the time span in which you want to plot the orbits, and then when you plot the longer period orbit, call it unaveraged, and then this conventional orbit plot, which is kind of fixed to some sampling frequency, a number of samples, you can see that there's a big difference. This is what the conventional monitoring will show you. And this would maybe wobble a little bit. The numbers will change stochastically in a way, but because the machine actually takes a longer period to make an orbit. This is what really happens. And it sees much more of the bearing clearance than you actually see. And when on a nominal power, when you combine those two plots, they're practically the same, you can see. So in the normal conditions, taking longer period or short, or you do as conventionally, it doesn't make any difference, right? So the factor, this is why we introduced the factor. We are basically measuring this, and we are dividing and when the number starts to grow, that means that there is low frequency wobbling increasing, right? So with these counterphase vibrations, let's get back to that. It's basically what we are seeing, that the machine is tilting, and also it starts to axially vibrate, all right? So we come to low frequency dynamics. Axial displacements, they all show the same frequency, but also what we've seen that the whole bracket actually moves. So if you put the accelerometer here on this spot, you can actually see that the whole structure vibrates, not just the rotor, but everything, even this bracket. And then those frequencies, because this is very, very big mass, it vibrates on 0.5 hertz. So these cracks are more than expected. It's something that has to happen in this area because this is the support position, and when this wobbles it goes up and down for 1.3 millimeters, and this machine has, I don't know how many hundreds of tons. That's very bad. All right. So, and it happens because what we think is, remember that axial thrust, when the rotor lifts and becomes unstable, the oil film breaks, and then what happens is that the whole structure starts to vibrate on self-excited vibrations. Why does it lift? We still don't know, but it does. This is the fact. And then the rope also occurs as a phenomena, which is also a result of that instability. And that instability, just because there's a lot of energy from water that cannot be transferred to the turbine, it has to be released somewhere. So basically it releases itself as a self-excited vibrations of the whole system. And that usually occurs on the lowest frequency of the system, right? So self-exciting vibrations always occur in lower frequencies, right? So this is the example where we put the accelerometer. It's on the bracket, actually basically monitoring the whole big wobbling, right? And so, because we are practically almost out of time, I'm gonna just wrap it up a little bit. So there's another question. What's the solution now? What can I do? I mean, this all happens and it's very good. We can measure it, but what do we do? I mean, so this is the question that we get from our customers and our partners that we work with. And then, to be honest, it's very little you can actually do if you have that problem. But only thing that you can actually do is map that zone, right? So you have to map the zone and then avoid working in it, all right? But should we allow some parts of zone to be, available for operation? Of course. So mapping the zone actually means analyzing the right data, which the right data is what I've shown, the correlation between the pressure, the thrust, the axial vibrations, the radial vibrations, and this will give you indication what's really happening. If I'm operating in that zone, are my orbits exceeding my bearing clearances? Is that all bad for my machine? How bad is it? In which parts of the zone is that most severe, and in which parts I can really, it's just a little bit worse than normal? And this is what you need to analyze and map, and then you reevaluate your risk of operating in your airflow zone, which area is, and you basically get a kind of intensity chart where I should operate, or where I should avoid and where I should operate. So you get a, let's say, kind of a fuzzy zone, which should be strictly avoided, and then you remap the allowed operating zone, and you give it to a dispatcher, because most of the machines, especially I'm talking about customers that we work with, they're operating machine from the dispatch center. So the dispatcher wants to know what's available and when he needs some power. So if he needs immediately 20 megawatts, is it allowed for this machine or not? Should I be working with this machine on 20 megawatts or not? So this is what we really want to know. But you cannot avoid the rough load zone. It's here. It's because of the design of the machine. But how can I really monitor it and put my alarms carefully so I can still I can increase the availability of my machine, right? Of course, there are countermeasures that can reduce the rough load zone effect. Let's say one of them would be blowing the air under the turbine. This is from one of our customers, and they've done some tests. And when you're blowing the air, there's basically better response. This is the displacement of the shaft. And when there is no air, you can see low frequency wobblings. When they blow air below the turbine, they basically break the vortex, and it's better. It's not the best, but it's better. But this again has some side effects as well. It's not a perfect solution because it lowers the efficiency. So again, there is a back, like it's not the best solution. So what should we do? I mean, again, there is no other way. This is better than nothing, but it's very hard to mitigate actually the effect of rough load zone, right? And then also another idea is that you correlate because you don't want to use it as much. You should you can correlate, make a feedback to the data that we are measuring, and then turn this on maybe if possible only when really necessary, rather than every time there is like a indication that they're working in rough load zone. Okay, so this subject is very interesting. So I tried to wrap it up in 30. Now it's 38 minutes, so I'm a little over the time. I'm sorry if I missed something. I'm sorry if I was not really, if you didn't really understand completely what I was trying to say. You can ask questions again, and you'll get this the slides probably available to you. So you can also contact us anytime if you have any more questions. So just to wrap it up, rough load zone occurs on Francis turbines. You need to install the right sensor configuration to monitor properly. And the idea is you cannot avoid it. There are countermeasures you can take, but the best is not to operate in that zone. And to be able to actually know what the zone really is, you should be monitoring online and basically make your own map for each machine. This is the best way we've seen so far working, and our customers gave those maps to dispatchers, and they basically use that to run machines and avoid operating in that rough area. So thank you very much for this. This is my last slide, and if you have any questions, I'll try to answer if I can. And I'll leave it to the coordinator to take your questions and run it to me.
Yeah, so we have our questions box or even the chat window. You can type your questions. I just wrote a message to everybody there, so you can type your questions there, and we'll take those questions. We give 2 minutes for everybody to write the questions and come up with those questions. Till you're thinking about your questions, I just have an announcement to make. So the next webinar is on DC ramp testing. This is kind of a high-pot stator winding evaluation tool that is used in the industry. So we will be doing this webinar on March 17th. Again, this is DC ramp testing, and you can find the details on our website about this webinar, or you can register for this webinar in advance if you find this topic interesting. Hey guys, 1 second.
Just for everyone, I did send out a copy of that link as well in the chat in case anyone wanted to have the link to sign up for the next webinar as well.
Okay. So we have a few questions coming in, guys. Please type in your questions. We are going to read them, and you know, hopefully we can answer them as well. So the first question is, how does low frequency vibration affect machine parts?
All right, just go back to the slide that I think I shown already. So I'll go to the first slide. So it affects it like this. Just a second. Like this. So it creates huge problems. But basically, low frequency displacement, vibration low frequency, when you turn it to displacement, if the vibration is high, let's say if you're measuring with accelerometer, you're measuring the velocity of the vibration on low frequencies, the number doesn't have to be really big, but when you turn it to a displacement, it's really, because when you integrate on low frequencies, the number grows. So in this particular case, if you would just have a overall number measured, then it would be like, I don't know, 0.5 millimeters or 1.23 millimeters per second, which is not really so high, but when you turn it to number, it becomes movement of 1.3 to 1.6 millimeters peak to peak. So imagine 1.6 millimeter doesn't sound much, but if you have 600 tons, which moves 1.6 millimeters up and down, cycles, that's really destructive. And if this machine's supports are these beams are very big, and they're very well supported in the concrete, and you get cracks like this. So it's devastating, I would say. You can even have the runner blade cracked as a result of operating in the rough load zone.
The next question is, how well aligned was the unit you studied? I'm wondering what impact the overall alignment has on these vibrations you presented?
The alignment, if I'm correctly getting the question, the alignment, the shaft alignment, it doesn't have to do anything with the low frequency vibrations. So shaft alignment, let me just try to find out. All right, shaft alignment would appear on 1x. Usually, if you have a dog leg or something, basically it's a slow roll vector, and it's related to machine frequency. Basically, we measure it on 1x. We go to a slow roll. You can slowly turn the machine, but in between one and another trigger, which is one rotation, you get that low frequency. Low frequency 1x. So the shaft alignment doesn't have to do anything with the low frequency wobbling. This is happening on subharmonics. These are not related to machine frequency. So if you see here, you have multiple turns, and it takes one, let's say one in 5 turns, you get the precession. This is the precessional movement of the shaft. So it's nothing to do with alignment. This shaft is perfectly aligned. When you go to low speed, there is no dynamics. But what happens is that machine tilts and moves like this on the low frequencies, basically like swirls around in a way. Yeah? So these two are not related.
Okay. Next question. When you come to a site, do you usually find sufficient number of vibration sensors and configuration, or do you need to install additional accelerometers?
We usually need to install additional accelerometers, 95% of cases.
Next question. Where should one measure axial displacement exactly?
So one measurement should be on a turbine cover. This will give you basically in a way of the lift of the turbine cover to the concrete foundations. So basically you're measuring from concrete foundations, you're measuring turbine cover, and then another one should be on a bracket measuring the oil film. So basically we're trying to figure out if there is a lift of the rotor to the bearing, which creates the oil instability. And the third one we usually put on top of the rotor, again on the concrete foundations, to see the complete rotor lift. So we get the turbine cover lift, which also sometimes blows with a pressure on the turbine. When you put the pressure in the turbine cover will grow a little bit. And then another one is we want to measure how much the rotor lifts to the bearing. And the third one is we want to measure how the whole structure meaning rotor and everything vibrates. And also we need the accelerometer in axial direction to confirm that as well. So 3 axial displacements ideally.
Okay, we have a few more questions here. So how to avoid working in rough load zone, and how to set up protection?
All right, so to avoid working in rough load zone means you just have to pass through it. There's no way you can completely avoid it, but you go to the rough load zone as fast as you can. So in this case, just run through it it depends, a couple of minutes, how fast you can. Okay, this is the power decrease, but I think I have maybe the power increase like this. So this is a typical from extracted from monitoring, just a typical 2-3 hours duration of the operation. This is the start. It happens quickly, and then you just quickly go to load, which is outside of your operating restriction, from 0 to, let's say, 70 megawatts, and then you put it on full power, which is 140. So you just pass through this and hope that vibrations, when you pass quickly, they do not have time to really develop. You just basically get out, and then it takes a couple of minutes. But each time you do that, you pass through these conditions, and then you really need to know what's happening, how severe that is, because if these are really, really big vibrations that occur, you just want to go as fast as you can, but you cannot avoid passing through that. So because it's there, so you need to actually get to the certain load, and then alarms should be set, as I said, in that operating zone when you don't want to trip your machine, but you still want to be certain that there is no damage to the bearings, for example, that your shaft is not hitting the bearings or something like that. So you would set up the alarms for that operating conditions on a higher level, but still to protect your asset, you know. And then when it gets out of that zone, you just put it on normal as per standard or as per your preference, depending on your machine and your basically your how you run it.
Next question. Most Francis turbines have a vacuum breaker valve that opens below a certain gate position. Have you looked into evaluating proper operation as a function of head and load, not just gate position, of the vacuum breaker valve to help add air to the vortex rope and help mitigate the magnitude of the vortex oscillations?
No, shortly. We didn't have a chance to do that. But that was a good question.
Okay. Is it self-excited, which comes from hydraulic parameters of turbine design, or a function of magnetic parameters? I mean the source of it.
The self-excitation comes from it's turbine related, not generator related. So it comes from the fact that the energy has nowhere to go, in a way. So the kinetic energy of water has to be turned, the potential energy of water has to be turned on the turbine basically to power through kinetic energy, and then it doesn't happen probably. So this is our theory. It's not confirmed. This is not just ours, but we discussed it with some people that have the same opinion. So basically, the energy has nowhere to go. It cannot be transferred to the turbine properly. So and then whenever you have more energy than the system can absorb, then it releases itself in self-exciting vibration. This is what self-exciting vibrations, how they occur. There is energy that cannot be absorbed or transferred, and then basically the easiest way is for the structure to start vibrating on its own frequency. This is what happens. But that own frequency here is the lowest. It's always the lowest frequency of the system. It's related to the whole structure, generator and brackets and turbine and everything. That's why it's so low. Again, this is our theory. Not our theory. This is what we think. It's not our theory. There are people that discussed it before, but this is what we think. Okay. This is what happened.
A few more questions, Osram. Have you looked into evaluating similar rough zone operating areas on blade type turbines?
You mean on the Kaplan turbines? I'm not sure if that's a question, but Kaplan turbines do not have. I mean, we have seen similar effects also in Kaplan turbine bulbs, actually, but because they have adjusted pitch of the blade, they usually don't have these problems. So we have seen it only on actually on one type of machine so far. Something similar happens there. In theory, that you can find it in theory in books that there is something called, again, you can call it rough load zone for the Kaplan turbines, but it's not the same phenomena as this one. It's different.
So the follow-up is meant fixed blade turbines.
Fixed blade. Okay, this is the fixed blade turbine, am I right? I mean, for the fixed blade Kaplan turbines, probably. No, we haven't had the chance to actually study it ourselves yet. But I know that some people have discussed that they're on fixed blade turbines, Kaplan turbines, which don't have an adjustable pitch, that they do have problems, and sometimes you can feel the vibrations even in the building.
Okay, we'll just take a couple of more questions. What is the process involved in mapping the rough load zone?
So basically, you need to have the data. So you need to have so here what we've done. We were measuring the head. We were measuring the power, and then we were correlating when low frequency vibrations occur. in combination of a head power and then a certain combination of XY head and power. There is a area where we did tests during with the online. Basically, we didn't do tests. Collected the data over a year with the online monitoring, and then we analyzed the data properly and thoroughly, and we came to this map. So it's a process of analyzing the data, collecting the data, and analyzing the data, because you need to get all these conditions. So that you can only have if you leave the machine operating normally throughout the year, and then the water goes up and down, the lake is filling up, and then basically we did this by analyzing the data when the low frequency starts to occur and in the combination of head and power. It's a process. It's not like something you can really do fast. You need to collect enough data to have enough points that you can actually call this. You see that it's now this is the extrapolated line out of these points here. So it's not strictly this. This is what we extrapolated through the points that we collected.
This is probably we'll take this as the last question. Anyways, if anybody has more questions, they can always reach us via email. And is there a particular spec of an accelerometer that you would recommend for measuring the rough load zone? Or
I think I mentioned it. It should be high sensitivity, meaning more than 500 millivolts per G or more. You have 1,000 millivolts per G accelerometers, which are better than this one. Why high sensitivity? Because all the accelerometers have the problem of signal over noise ratio on low frequencies. That's the piezo crystal characteristic. So higher sensitivity probes, usually more expensive, of course. So we usually, for online monitoring, we use 500 millivolts per G, which is quite good. Now there are 1,000 millivolts per G actually at a very acceptable price you can actually get. And then the other thing is that it has to have a low cutoff frequency, low enough so you can actually get the response good enough. Again, I'll just mention one thing. The phase measurements on low frequencies are not as accurate. So when you reach on the accelerometer now, you don't have time to go into details, but the closer you get to this frequency, the phase distortion gets bigger in a way. So it's not, but it's still accurate enough to get a decent analysis out of it. And then for this low frequency wobblings, it has to be as low as it can go. So basically 0.1, 0.2 is what you can find now on the market. The upper frequency is not really, it doesn't matter. It's the low frequency. So as low as it can go and as high as it can go with the sensitivity. And then it doesn't matter which brand it is. They're all pretty much the same. They're commodity products. There are better and worse, of course, but yeah.
Okay, perfect. So we'll wrap up this presentation here. And thank you, Ozren, for,
thank you.
We had a few thank yous as well in the questions. So thank you so much for this presentation. And yeah, we'll see you March 17th for DC ramp testing. Thank you so much, Will, for organizing this as well. Huh?
Thank you very much.
Thank you, guys. A reminder as well for everyone, we're going to email out a copy of the recording and the webinar. So you guys should get that usually within 24 hours. Any questions, you can reply directly to that email, or you can give us a shout at info@qualitrocorp.com as well.
Okay. Thank you very much, and have a nice day. Bye.
Yeah.
Okay. Thank you.